Professor, my name is Ramtin Abulfazli with the student ID 1014192226. I'm going to explain the first assignment line by line um, from what I have coded. So first of all, we are importing the fashion MNIST dataset. It's very similar to MNIST dataset, however, it's more complicated because it has more different clauses, which requires um, way more pixel amount. So it has like 28 by 28 pixels, which is harder to detect. First, we're loading the data into train and test images and labels, printing the dimensions. So what are the dimensions of training image? We can get that with the shape method. And then for the length of each training or test labels, we can just use len method. Then we are getting the some of the train and test labels, which we can just achieve that by using this basically array from 0 to 10. Then we are getting the fifth train images. So the fifth that has 28 by 28, this is how it looks like as of like raw data and all numbers. Then if we would like to create the image from that, we can just use imshow, this method from matplotlib, imshow image show. So we would like to shape the fifth image, and the color map is gray. And this is just writing the train label, so which has the number 2 train label. If you would like to find out what is this train label is actually referring to, we can just write this hard-coded thing, which is already out. Like we know each one of these label numbers are referring to what kind of clothing. That's why when we hard-code it, we can find out which one actually it is, because the reason why we cannot do such a thing in the training model is because machine learning deals with numbers and not strings. So this is human understandable, and the other one is machine understandable. This is for the 500 one. The same thing. Same thing. This is a pullover. Then we would like to create a deep neural network, different layers. For that, we just import the sequential model, assign it to a variable like my network, and then we would like to reshape it. We would like to flatten it, because in deep learning model, in the deep neural network, in different layers, neurons cannot take matrices. They should only take one-dimensional array. That's why we have to reshape it to one-dimensional, and when we are multiplying, like we're saying 28 by 28, so all this multiplication, which is the total 784, will be stored in one single dimension array. After reshaping it over here, we are normalizing it. Normalizing it because the range from 0 to 255, if we divide it by 255, it will give us a range between 0 and 1. And the reason why we are normalizing it is because normalization results in making sure that nothing is affecting our model training more than what it should. So everything has the basically same effect, or the effect that it should have on our model training. Then we are defining different layers in this neural network. The first one has 512 neurons. The activation function is ReLU, and this is the number of input layer, as I said, the one dimension that we are inserting in that layer. The second one has 128 neurons, the same activation function, and in the end, because we would like to get the results that which one of these 10 different labels this neural network thinks our training set is, and give us a prediction on the label. We are using a softmax algorithm. Softmax algorithm is for classification models which has more than like two, like it's not binary, it's multi-class classification basically. Then we are compiling our neural network by using an optimizer, Adam optimizer, and sparse categorical Carson-Turvey as a loss function. After that, we are training this model. So it may take a bit to be trained. I wish I wouldn't do that because I already had the results. So it will give us an accuracy, and then over here we are trying to compile this model with another optimizer to see the difference, to see how different the accuracy it will be. And so this one's accuracy will be actually higher by 0.01 than Adam optimizer. And in the end, when we are evaluating our model, we had two questions over here. So how do we compare fashion MNIST with what we learned in the class using MNIST? The comparison is MNIST has 10 numbers 0 to 9. It's easy to detect, it's very obvious, like which one is 0, which one is 1. However, fashion MNIST has different shapes, has different pixels. It's hard to understand for our model. It's harder, at least, to find out which one is close, which one is dress, which one is pullover. So it's more involved. What can we infer from the differences in accuracy? Basically, the accuracy between MNIST and fashion MNIST, but as I said, fashion MNIST is harder for the model to be understood and be basically predicted. However, MNIST is very easy to detect which number we are getting. So when we are using this evaluate method over here, we are evaluating the test. So we are getting test loss and test accuracy. Test loss refers to what was the loss function of our test. So the lower the loss, the better our model has worked, because it's saying the difference between the actual label and the prediction is less. So the lower the loss, the lower the difference between prediction and label, which what we want. And the test accuracy is saying how accurate was our correct predictions compared to actual correct labels. If it's overfitting, I don't believe so. I think for overfitting, we have to have the training accuracy and loss as well to compare test and training set. However, the test loss is very regular. It's not too low, it's not high. And the test accuracies are also not very high and not too low. So it's very reasonable, this one, and therefore I cannot say it's overfitting. So thank you for listening. Have a great day.